So when you talk about these three components, the three components are bias, variance, and irreducible error. Irreducible error. A typical prediction error will have three components: bias, variance, and irreducible error. Now, let us look at the irreducible error first. Irreducible error cannot be reduced regardless of what algorithm is used. So there will be always an irreducible error in your prediction error, which cannot be eliminated. There will always be error. No matter which algorithm you use, no matter how advanced algorithm you use, this irreducible error will exist. Now, this error generally comes from, this error originates, from wrong framing of business problem, framing of business problem, and caused by unknown variables and factors. Because of unknown variables and factors, also this irreducible error will occur. Okay. Now let us go to the next error, part of the error, bias. So bias are simplifying assumptions. Bias are your simplifying assumptions made by an algorithm, to make the target function or the cost function easier to learn. Simplifying assumptions that need to be made for the algorithm to work properly. Regression has this thing. So parametric algorithms like multiple linear regression, binary logistic regression, have assumptions that must be met before running the algorithm. There are assumptions: no multicollinearity, linearity, sample size related, dependency of y-indexes. All these things are assumptions which need to be met before we run the algorithms. Linear algorithms have high bias, which helps them to learn faster. If you give properly processed data to a multiple linear regression algorithm, it works very, very fast. If you give data which is not processed properly to a multiple linear regression, it will take time to run and also will generate a lot of errors, or it will definitely misfit. When I say misfit, it will definitely underfit. Underfitting is a critical problem that occurs when your basic assumptions are not met. Similarly, overfitting also occurs. Because of certain assumptions, overfitting will occur. One of the most important assumption that leads to overfitting is multicollinearity. The most the most problematic assumption that leads to overfitting problem, like in yellow taxi. If you included fair amount and total amount, your R square is 99, which is too good to be true. What was the preferred range for R square? 0.60 to 0.95. But when we ran the yellow taxi example with both fair amount and total amount, we got R square of 99. But when we did the correlation analysis, we found out the correlation between fair amount and total amount is 0.98, which clearly indicates multicollinearity issue. So I removed fair amount from the model. The R square directly fell to 0.599, or it is 0.60. If you round it off, it will be 0.60. That is the biggest change. One variable, by removing one single variable, we came from 99% R squared to 60% R squared. That is the problem which is created by multicollinearity. So if you run a regression algorithm, first do a correlation analysis, identify multicollinear variables, and remove them beforehand. Or if your algorithm is overfitting, it is definitely a multicollinearity problem. Okay, so that is what we found out. So bias are such assumptions. No multicollinearity is an assumption which is a bias in multiple linear regressions. There will be low predictive performance. The predictive performance for this high biased algorithms. The predictive performance of multiple linear regression compared to decision tree is always good or bad. Which is better, decision tree or linear regression? Decision tree. Decision tree by itself is a problematic, overfitting. But if you control the depth of the tree, decision tree is better than linear regression. By itself, decision tree is problematic because it will definitely overfit. But the predictive performance of a decision tree is always better than the multiple linear regression. We have calculated RMSE multiple times of regression algorithm and decision tree. And most of the times we found out that decision tree RMSE is lesser than linear regressions. So this high biased algorithms like multiple linear regressions, they have low predictive performance. Their predictive performance is low compared to the non-parametric algorithms. Particularly when they fail to meet the basic assumptions. When the basic assumptions are not met, then we have this predictive performance issue. Low bias means few or no assumptions about target or dependent variable. Low bias means few or no assumptions. See, in decision tree regression, the basic assumption must be the dependent variable must be numerical. There will be some assumptions. There is no model without any assumption. If you want to use decision tree as a regression mechanism, what is the assumption? The dependent variable must be numerical and continuous. When will you use classification decision tree? When the dependent variable is non-numeric, either binary or multinomial. That is basic. A few assumptions will be there. Or some scenarios like no assumption scenarios will be there, which are AutoML algorithms. AutoML algorithms will automatically read the data structure and then they will implement. Neural networks and very advanced algorithms, we call them as AutoML. AutoML is now coming to picture, but AutoML still has a lot of time to reach those levels which are needed for man. AutoML means you don't need to give any algorithm anything, just dump the data, it will decide. It will identify the dependent variable also. No, it is not like unsupervised algorithm. In AutoML, we generally specify the target variable. Or it will suggest the target variable, you have to simply say whether it is yes or no. So, if you are looking at AutoMLs, the most popular AutoML is IBM Watson. IBM Watson is the AutoML. In IBM Watson, you just need to dump the data. It will create its own hypotheses. You just need to identify a dependent variable. It will create its own hypothesis. It will create its own hypothesis statements. It will run the test. It will give you what you call exploratory data analysis automatically. It will frame the questions. It will answer the questions. Everything is automated. IBM Watson. But the cost of Watson is $1 million. It's very, very high cost as of now. AutoML is not cheap as of now. There are certain startups in India that are working on AutoML to make it less costly, but there is still time to happen. So low bias means no or few assumptions about the dependent variable. High bias means many assumptions about target or dependent variable. There will be many assumptions. In high bias situation, you will have many assumptions that need to be met, particularly on the dependent variable. Particularly on the dependent variable, also called as target variable. There we have this. Now, high bias machine learning algorithms, like I told you, linear algorithms. All the linear algorithms are high bias ML algorithms. The MLR, the multiple linear regression, DLR, binary logistic regression, are all high bias ML algorithms. Multiple linear regression, logistic regression, particularly binary. Are high bias ML algorithms. Low bias ML algorithms. Low bias ML algorithms. Yes. Tree-based models like decision tree, random forest, TBM, and KNF. K nearest neighbors is also considered as a low bias. Even SVM. SVM is also considered as a low bias ML algorithm, support vector machine. So this is the context of bias. All right. Now the second part is variance. Variance is amount of deviation between amount of the deviation caused in dependent variable or target variable when there are minor to major changes in the input variables or independent variables. So variance is the amount of deviation that is caused in the dependent variable or the target variable when there are minor to major changes. When your data which you are passing through the algorithm for the second time, be it a test data or a subset of your trained data in k-fold cross validation, will you get the same R square? Will you get the same accuracy? You will not get. So whenever you pass the data, a part of the data which you randomly selected as test data into a trained model, there will be certain amount of deviation. The R square will be less and the accuracy will also be slightly lesser. Slightly if there are minor changes. Or if you have randomly subsetted, you are doing validation, cross validation, where you randomly subset the data. And then those random subsets you pass through the trained model, you will get different R squares and you will get different accuracies. It might reduce or it might increase. That we call it as variance. The deviation occurs when there are minor changes to the data to major changes in the data. Sometimes very few changes will be there in the data. Take, for example, you randomly selected some test data, which will have some sort of change in the data. So your accuracy in RMSE will, R square will reduce. But if there are major changes like skewness, like kurtosis, like outliers, these are like major changes, right? Suddenly, till now, you're dealing with only data with insurance claims of 50,000 rupees only. Suddenly, you start insurance claims in your data more than 50,000. And that data is around 20%. Will your existing model work? Because you have suddenly got outliers. You built an earlier model with maximum claim amount of 50,000 rupees. It is now happening with all insurance companies because government has drastically increased the COVID claims. Government said minimum is 2 lakhs. COVID claims can be up to 2 lakhs minimum to maximum 10 lakhs based on the amount of premium because COVID was not there, right? When you bought a medical insurance policy in 2018, will there be a COVID coverage? No. So COVID suddenly happened. In 2019, government could not decide the claims because nobody knows what was the cost, what was the variance and all. In last year only, they could come up with the minimum claim and the maximum claim. Now, suddenly, COVID is a pandemic. No matter how much you try, your medical insurance claims will be there. And you will have claims in the range of 5 lakhs, which you normally don't see in a normal year. If there is no COVID, hardly you will see above 1 lakh claims, very few. 10% or 20% of your total insurance pool because of bypass surgeries or kidney problems or kidney stones. These are high cost procedures. But most of the procedures are less than 1 lakh. Even stunting in heart, one stunt heart procedure is less than 1 lakh, 75,000 to 80,000. When you're going more than 2 stunts, then your cost will go up to 2 lakhs. So, but now what is happening with COVID? The minimum itself is 2 lakhs. ICU charges, everything, right? COVID is very, very non-operative, but has a lot of cost in terms of ICU. Why it is cost? Because of the ICU. If the patient isn't there for 10 days in an ICU, per day ICU cost of government approved rate is 15,000 rupees per ICU. 10 into 15,000 is 1,50,000. Government fixed, right? 15,000 per day for ICU, including ventilator. 10 into 15 is 1,50,000. But if you use in private hospital, 30,000. Double that, right? 10 into 30 it is 3 lakhs. So when you have such data, suddenly coming data which has high variance, when I say variance, skewness, kurtosis, outliers, which are all can happen in COVID insurance claims. Now COVID, because of COVID, all insurance, medical insurance companies are forced to raise their premiums. Their whole insurance pools, which they create, you know the pool, right? The whole success of the failure of the insurance depends on the pool. The pool should have high risk candidates, medium risk candidates, and low risk candidates. The ratio is 70% low risk, 20% medium risk, 10% high risk. They create a pool. They collect all the premiums from such people and put it into a pool. And they hope most of the low risk people will claim, very few high risk people will claim, and the insurance company will keep the claim, what you call premium money as profits by paying some amount of claims. But what is happening with COVID? All these rules are vanished. Even a low risk guy can also get COVID, right? And then the claim is gone. Now the insurance industry is now struggling in India, not only India, across the world. Now the pools are gone. You can't assume that the young guy will not claim. If I have 70% of my policies sold to the young persons, I don't expect the major claims. Only the Indian road accident rate is only 8%. Out of 8%, major accident rate is only 3%. In India, major accident rate in two-wheeler roads in city of Hyderabad is only 3%. When I say major, multiple fractures, and then hospitalization with lot of what you call implants and all, that is only 3%. Most of them are fractures, simple fractures, guy falls from the bike, hand broken, leg broken, those scenarios. But look at the multiple fractures. Multiple fractures, high-speed bikes. Again, that is a classic example. KTM. High-speed bikes are there, right? Now, because of high-speed bikes, the young people are now at more risk of higher insurance claims. Because if a guy on a KTM bike goes through an accident, you can imagine, will he come out of the hospital with one single fracture? No. There will be multiple fractures, lot of rehabilitation, lot of medical costs, implants costs, all these things put together, it is very, very big. Now, what is the primary problem? Government wants money, tax money, import duty. They allowed all the bikes into the city. You have 250cc bikes, 350, 500cc bikes are also running on city roads. You cannot use 350, 250cc on road. It has to be used on a race track. You know, on a race track. But our guys use them on roads. Look at the amount of risk they are taking. The risk is very, very dangerous risk. One simple pothole at 180 kilometers at 200 speed is gone. If you are at 80, 90 kilometers, you will not have that problem. You might fall or your bike will skid, okay, some rashes, scratches will happen. But when you're at 180, 200 speed, a small pothole is enough for you to take you to the heaven and come back. Right? Knock the door of heaven and come back. Right? They're not disclosed that Saidaram says, yeah, he went through multiple fractures, he had severe injuries. Otherwise, why would that guy will be in hospital for 1 month if he is not suffered minor injuries, He was in neural stop. The impact, the brain got disturbed. The neurological shock happens when the brain gets jittered in the skull. Because of it, the blood flows and the bleeding will happen. When that happens, only option is you have to put them in induced coma till the blood goes up. So all these things will happen. Such variance in data is problematic. See, COVID is not only accidents, defaults, personal loan defaults. How many people defaulted on personal loans because of COVID? Very high. Home loan defaults, COVID, very high. So variance is not the biggest challenge in data science. Suddenly you see data with huge variances in terms of skewness, kurtosis, outliers. Very big skewness in it. So now all the models have to be fitted with such pandemic issues. Now the new variable which has to be taken into consideration for insurance industry is pandemic. Can they ignore pandemic for next 5 years? Not. They have to rework their models. Existing models will fail completely on such data. They have to rebuild the model from scratch. With highly skewed data, all their biases are now gone. The basic bias that a young person has a lower risk is gone. That was the fundamental, right? A young person will have lower risk, middle-aged person will be moderate risk, high-aged person will be high risk. That is the bias or assumption they were using earlier. Now there is no such bias. All are equal risk. Even children are at risk. Right. So when you have such scenario, you have to rework your whole model backwards. And then you have to completely create models from scratch with this new data. But COVID, all those things are done. You have created a pool. There is nothing wrong. Your insurance pool which you have created for the set of 1,000 people is the best with medical checkups and all. But what is the situation from 2019, 2020? See, I am telling you the 70-20-10 ratio is the one which every insurance actually will do. 70% in the pool should be young people under the age of 30, 30 to 50, 20%, above 50, 10%. They collect the premiums. So 1,000 people, let us say they are collecting 5,000 premium. So the pool comes to how much? 5,000 into 1,000, 5 crores, right? 5 crores is 50 lakhs. 5,000 into 1,000, 50 lakhs. Assume it is 50 lakhs. Now, we expect the claims to be half. Generally, for the insurance companies, the claim ratio should be less than 20%. That means out of 50 lakhs, they will assume a claims of 10 lakhs. Another 10 lakh is administration costs, salaries, and the regulatory fees, taxes to the government, and all those things. So 30 lakh is their profit. Huge profit. But now what will happen? Their claims are beyond the pool amount. Pool amount is 50 lakh. Now they have claims of up to 3 to 4 lakhs. Now who has to bear that loss? The insurance company has to bear the loss. That is why the health insurance companies are on the verge of bankruptcy. They are asking government to fix lesser claim amounts, but government said 2 lakhs is the minimum you have to pay. Yes, popular politics, right? 2 lakhs. Even though the yesterday Supreme Court said till March 30th, people who have died, March 20th, people who have died of COVID can claim. Can claim till next 2 months. So when you have such scenarios, insurance companies will be in trouble. So that situations you have to have. So variance is a big problem in data science. So variance is another example is IT industry, social media. Suddenly you will see subscribers increasing. Suddenly you see subscribers falling. YouTube, classic example. If the video is popular, it will have millions of subscribers it goes up there. But after some point, what happens? It drastically falls. Hardly thousands of people will listen to the song on the YouTube. But initial launch to first 30 days, there will be very, very steep curve of people viewing, listening, and all viewing will go up last. But once it reaches to the top level, then it will fall. Every song, no matter how much popular it will reach a peak and then it will fall. And people in thousands will reach, not in millions. People in millions will not listen to the song after a certain point of time, right? That is another problem YouTube is facing. Because YouTube views, how to calculate the views, and based on the views, you will calculate the ad rates. AdSense rates are calculated based on the views. Now the YouTube is still struggling. They have to fix the advertising rate based on the views. Now, views in a day will change drastically. In the morning, 1 lakh people might have watched the video, but by afternoon, evening, it might fall down to thousands. Now, how do you fix an ad rate? You have to fix an ad rate based on hours, right? Not on the whole day. That's how we have to come up. So these sort of things will be there. Variance is a very big problem in data science. So that scenarios. See, even in private hospitals, in the beginning of the month, the X-ray machine is used very widely. There is a huge demand by outside the X-ray department. After 15th and 20th, will you see the same set of people standing outside the X-ray department? Right, you won't see, right? First to 10 days, month beginning, people have money, they go for medical checkups and they'll take their family members, whatever diagnostics, CT scans, huge crowds will be there. But after 15, in the same hospital, same doctor, his number of CT scans or X-rays will drastically fall down. No doctor will have the same type of thing, right? Because people will not have money post midterm, and these are high-cost diagnostics. So how will you plan the usage of the machine? And you know how much it costs? One CT scan machine, 18 to 20 crores. And 18 to 20 crores, if you want to get back that money, how many years it takes? 4 to 5 years. You cannot get it in 1 year, right? That money. That means you have to write the CT scan for every person, every patient who is entering the hospital has to go to CT scan all 30 months of the day. Then next month the hospital will close down. People will not go there, right? So you have to manage that thing, right? Doctors have to manage it. They have to make sure the machine is accounted for, and also make sure that people don't find it things. So the variance of data will also be there in this thing. So medical in US also we have the same problem. Doctor bills in the beginning, you know, NHS and all those things, huh? UK, NHS, American Medicare, Medicaid systems, the bills which come in the first 15 days of the month are very high compared to the last 15 days of the month. It's an anomaly. And we have to build a model with such sort of anomaly or variance. That has to be included in your model building. Otherwise, you are losing a trend. See, there are exceptional events which do not happen on a regular basis. But a road accident can happen daily. See, accident on a road, see, on an average in Hyderabad, reported accidents are 80 to 100. Unreported accidents per day is 80 to 100 in the city of Hyderabad. 80 to 100. This is 2020 when the traffic commissioner said 80 to 100 is what we deal on the reported case file, FIR registered. What about unreported? It will be 2 times or 3 times more than that. Small dents, small what you call tail lights breaking, or those things. People won't register case for such things, right? They will just do the solve. Or a person has fallen and he will go on his own, get the medication done himself. So variance will always be there. So how we deal with the variance is what you guys will face a lot of challenges in real-time data science. This variation is a very big problem. And in any type of data, you have this variance. Climate change data. You know, you might have seen TV right now, right? The Antarctic ice is melting, oceans are rising. So variance is there. We can't do anything. Temperatures, right? Normal temperatures in the month of April, we have already crossed it. Now, the predicted temperature for May is 50 degrees compulsory this month, this time in Hyderabad. 50 degrees centigrade. Last time we didn't go, we went up to 49.2 or something. This time they are saying 50 degrees guaranteed. Now 50 degrees guaranteed means what? So I'm telling you, variance. These are all examples of variance. Okay. So you will see two types of scenarios. Low variance. Low variance is small or marginal changes. Small or marginal changes in the input data that lead to smaller changes in target prediction. Very small variance, smaller marginal changes. Then you have high variance scenario, where we have large changes to data. The input data, in the input data, that lead to larger changes in target prediction. Ukraine war is a big variance, right? Ukraine war is a big variance. All products, commodities, it's gone. Wheat, 30% supply of the wheat comes from Ukraine and Russia together. 18% from Ukraine, 12% from Russia. Now Russia is banned, they can't export. 18% Ukraine is in war, they can't do anything. So if you 30% of your supply goes down, what will happen to your price? It will increase. So variance is not smaller here. 30% variance in a supply is a very high, right? How will you plan your supply chain management? Plus or minus 5%. Or worst case scenario, 10% change in the supply. Either supply goes up by 10% or supply goes down by 10%. That is how you develop a logistic plan and you demand. The supermarket chain, Reliance or all these things will based on 10% increase in prices or 10% fall in prices, they will make their stock. If the Reliance finds that 10% prices will go up, they immediately go to the market and buy the wheat and store it in their godowns. If they feel that in the next month the price will go down by 10%, will Reliance go to the market and buy it now? They will wait for next month. They'll keep the godowns idle. They'll keep the godowns empty. And when the price goes down to less than 10%, they'll go to that and buy. Now, what is the variance? We're talking about 30% variance, 40% variance in prices. No matter how much demand forecasting you have done, these sort of challenges will create big problems. Vegetable oil, right? Why do you think people are running for vegetable oil? That cooking oil. Because of this only, people will go, normally the guy hardly buys 3 liters in a month. Now because of price increase, he is ready to buy 10 liters. That is again, we didn't expect that to happen in our data, right? Currently the store on a day is selling say 100 packets of oil. Now you see they are selling 300 packets of oil and placing another 300 packets on order. What will happen to your demand forecasting? It is gone. So everything, the variance in thing, when you have a planned variance, you always have variance in our mind, plus or minus, something will keep in our mind. But if it goes beyond the plus or minus which we are expecting, then it's a problem. That's what we do, right? When you go for shopping also. Okay, 10,000 rupees plus or minus 2,000 rupees. That is how we go, right? No matter how we go with 10,000 budget only, plus or minus 2,000, we always go with a thing. But if you are going into plus or minus 8,000, 5,000, that means you are causing a bigger variance in your budgets. That is the problem. So smaller changes will lead to bigger problem. Now, when you have variance issue, non-linear machine learning algorithms are highly sensitive to the variance in data, in input data. They are very, very sensitive. They are highly sensitive to input in to variance in input data. They have a lot of flexibility. Decision tree has a lot of advantages, but the way it reacts to some basic changes in data is very, very bad. Whereas linear machine learning algorithms deal with variance better and are less sensitive. They are less sensitive to changes in input data. They are less sensitive. They are also sensitive. Not that they don't react. They will also react, but the reaction is minimal or it is less. Now, the goal of machine learning algorithms try to achieve, machine learning algorithms will try to achieve low bias and low variance. Hello? I'm in a class right now. Please call me after 6 o'clock, okay? Machine learning algorithms will try to achieve low bias and low variance, which is very difficult to do. This is a very, very, very difficult thing to achieve. So this is the trade-off. This is the trade-off generally we see in machine learning. The blue line represents bias, the green line represents variance. So underfitting zone, what is happening in underfitting zone? Low variance, high bias. In underfitting zone, low variance, high bias. So underfitting zone, low variance and high bias. Overfitting, high variance and low bias. High variance and low bias. Now, in real-time data science, this is what we generally have to constantly target for. We have to find the middle zone. We will target R square of 80 only. We don't even target R square of 90. Because if you target for R square of 90 and all, there might be a question of what you call overfitting problem might occur when your variance will drastically drop when you do cross-validation. Rather, we try to achieve a 0.80 R square and try to hope the cross-validation also stays at that level. So you have to find a middle path between underfitting and overfitting zones. If you don't find this, then it's a problem. The problem is you need to find a balance between underfitting and overfitting. Okay. So basically, underfitting is where underfitting is where the ML algorithm, the machine learning algorithm, fails to capture the underlying trend or pattern in data. Underfitting algorithm is the where the machine learning algorithm fails to capture the underlying trend or pattern of the data. So the ML algorithm does not fit on the data, and it generally happens when there is not enough data available and can be corrected by increasing rows or decreasing columns. What are rows? Observations. You try to increase your observations or you try to reduce your variables. This is one easiest method of dealing with underfitting. Increase the data in terms of rows or reduce the data in terms of variables. We can reduce variables by feature selection or by selecting certain variables, we can reduce the number of variables. We'll talk about the feature selection post break, how we select variables. So if you are looking at techniques for reducing underfitting, if you are looking at techniques for reducing underfitting, increase data, both rows or reduce variables or features is the primary one we try to target. We try to increase the rows. If you can't increase the rows, we reduce the variables by selecting the specific variables. Remove noise from data like skewness, outliers, etc. You have to remove the noise from the data. Deploy feature selection methods or dimensionality reduction methods. deploy feature selection methods, or use dimensionality reduction methods. Dimensional reduction means it combines variables into components. It does not delete variables. Dimensional reduction will combine variables into components. So no deletion. Variables will be combined into components. Actually, they're combined into factors. We call them as components. Component 1. Once you run the dimensionality technique, no longer it will be variables. It will be component 1, 2, 3, 4, like that it will be. It will be renamed because they are not single variables. They are multiple variables in one component. That we need to understand. Now, overfitting. Overfitting is when there is drastic difference between trained model and tested or validated model's performance. There's a huge difference between the trained model performance and the tested model or the validated model performance. Big change in R-square or big change in accuracy. When I change, fall or decrease. Drastic reduction or drastic fall in R-square and accuracy. That we call it as overfitting. Large scale data has overfitting problems. When you deal with machine learning at scale, we use for big data these days machine learning at scale, like our yellow taxi data. 28 lakh rows, or when you are looking at millions and millions of rows of data, you will definitely see this overfitting problem. Large scale data has overfitting problems. Non-linear algorithms suffer from overfitting. What are the non-linear algorithms? Like decision tree. Decision tree suffers from overfitting. Even KNN also suffers from overfitting. So techniques for reducing overfitting will be reduce the data by sampling techniques. Not we have undersampling, right? Random undersampling is there. You can do the sampling techniques. You can do stratified sampling. You have a lot of sampling techniques which can be deployed to reduce the data, but it does not lose its trend and patterns. Okay, so in neural networks we have called GANs. Generally, adversarial neural networks are there which help us to reduce the data without losing the trends and patterns. GANs create synthetic data, also reduce the large scale data without losing trends and patterns. The biggest thing we use in regularization techniques like LASSO, RAGE, and Elasticnet are used for reducing the overfitting. Regularization techniques will be used. You can also reduce the model complexity. Sometimes, instead of building a more complex model, remember max depth 12 is a complex model, max depth 6 is a less complex model. By reducing the depth of the tree, we can reduce the complexity of model. By reducing the layers in neural networks, we can reduce the complexity of model. So that is also a very interesting thing in overfitting problems. So these are the broad techniques in underfitting and overfitting. And we have seen a lot of questions being asked in interviews on this underfitting and overfitting. The interview questions which I have forwarded to you, almost all 50% of the questions have this overfitting, underfitting problem. The question related to either overfitting or underfitting. So please by heart this underfitting and overfitting concept. Okay. So we'll break and then we'll come back after 10 minutes. And then we'll talk about the regularization techniques. Okay, so we'll talk about regularization techniques. All right. So regularization techniques. Are also called as penalized regression techniques. Penalized regression techniques are used to tackle overfitting problems. Are used to tackle overfitting problems. Regularization techniques are also called as penalized regression techniques, are used to tackle the overfitting problems. Regularization prevents overfitting by adding a penalty term lambda, or also called as alpha in Python, to the sum to the coefficients or to the regression object, or the coefficients of the regression model. Yeah, a penalty or lambda will be what you call multiplier. Actually, it is used to multiply the value. In some cases it is added, some cases it will be multiplied. So I'll tell you what it is. So basically, the idea is to bring the coefficients to 0 or close to 0. The idea is to shrink the coefficients to 0 or close to 0. If a coefficient in regression becomes 0, what is its effect on dependent variable? If a coefficient in a regression model is 0, what is its effect on the dependent variable? There is no effect on the dependent variable. Thereby, the variable will be deleted from the model. Automatically, the variable will be deleted by the regression object itself from the model. If the coefficient is reduced to a smaller value, what will be the overall effect on the dependent variable? A smaller effect on the dependent variable. Because how do you interpret coefficients? One unit increase in a particular variable will lead to increase or decrease based on the mathematical sign of the coefficient. That much value increase or decrease in the dependent variable. One unit increase in the independent variable will lead to the positive or negative coefficient. The negative means it decreases the dependent variable by that much. Positive means it increases the dependent variable by that much. So that is the interpretation of coefficient. Okay, so that is the interpretation of the coefficient. And the mathematical of coefficient is very important. If it is positive, it has a positive effect on the dependent variable. If it is negative, it has a negative effect on the dependent variable. Positive increases the impact on the dependent variable. Negative decreases the effect on the dependent variable. Yeah, lambda is a common metric. Lambda is a common metric. We three different lambdas are there. We will talk about it. So the regularization works by using this lambda or penalty to either shrink the variable number of variables, shrink the number of variables, or hello. डाल सकते हैं सर. Visiting faculty in yours. Or you have visiting faculty in your ask. ठीक है. Okay, yes, sure. Dr. Rajesh Prabhakar Kaila, I am visiting with you. Already ACT में है मेरा. You can do because I have done a lot of FDPs. ठीक है. Okay. ठीक है. Okay. So, shrink the number of variables or reduce the complexity of variable by shrinking the coefficient. By shrinking the coefficient. So regularization is a very powerful method which is used in real-time data science also to either eliminate variables or reduce the variables or reduce the complexity of models. Now, the first regularization method, we call it as LASSO regression. LASSO stands for least absolute and least absolute shrinkage and selection operator. LASSO means least absolute shrinkage and selection operator, also called in machine learning as L1 norm. In machine learning, we call it as L1 penalty or L1 norm. L1 penalty or L1 norm. LASSO adds, हाँ जी सर, अभी कर देता हूँ. So LASSO adds a penalty or lambda to absolute weights or coefficients of regression model. Absolute. LASSO will definitely make some of the coefficients 0, thereby which one? Some of the coefficients. Some of the coefficients. Some of them, not all of them, some of the coefficients zeros, thereby reducing the number of variables and also works as feature selection or variable selection method. Variable selection method. So LASSO is a feature engineering method or a variable selection method. LASSO is widely used to reduce the variables because it makes some of the coefficients zero. It definitely makes some of the coefficients zero. LASSO does not work well with multi-collinear data. So you have to be very careful. LASSO has a problem. The only problem with LASSO is data is highly multicollinear. It does not give you the reduction in variables. It does not make variables coefficients zero. But if it is a normalized data, some of the coefficients will be made equal to zero. So if you give X number of variables to a LASSO model, you will definitely get X less, X minus back. It will definitely make some coefficients equivalent to zero. So the objective is regression sum squares model. Generally, we call it as sum square model, right? Plus lambda into sum of absolute, not sum of, absolute value of coefficients. Absolute value of coefficients. When I say absolute value, what do I mean by? it will ignore the mathematical sign. It will ignore the mathematical sign. See, the statistical name of MLR output is regression sum square model. You remember the regression output in R? What is F? Mean square error divided by mean square residual. What is mean square error? Sum square error divided by n minus 1, n minus k. Sum square residual is mean square residual is sum square residual divided by k minus 1. You remember the various formulas that are used in regression calculation? Sum squared regressions formula. There are formulas, right? See, R square is 1 minus SST by SST. SST is equal to y minus y hat whole square. Sum of squares regression is x minus average of predicted values. X minus average of predicted values whole square. Sum square errors is y minus predicted whole square. Sum square total is SSR plus SSE. So we call regression also as sum square object. What we call regression sum square object, because there are a lot of SS calculations here. So these are the back-end calculations of multiple linear regression. Remember, x transpose multiplied by x to the inverse. Then we calculate the predicted values. Then we calculated the average predicted values, SSR, SSE, SST. And from there, you calculate R square, adjusted R square. So these are various formulas which are there. See, F MSR by MSE. Degrees of freedom. SSR by degrees of freedom. MSR means n minus k. This is k minus 1. N minus p minus 1, which is MSE. This is number of observations minus variables minus 1. This is p is your variables. So we have all this calculation and regression, right? Significance test calculation, degrees of freedom. So all this in multiple linear regression, you get a lot of output. That object we call it as statistically sum square object, regression sum square object, or regression sum square model. RSS object or regression sum square model, because there are a lot of sum squares which are calculated in the value. So the whole output we call it as RSS object. Okay, regression sum square object or sum square model plus lambda into absolute value of coefficients. Now, if lambda or alpha is equal to 0, you will get same coefficients as simple as a linear regression model. If lambda or alpha is equal to 0, you will get the same coefficients as a multiple linear regression model. If you say alpha is equal to 0, it is nothing but the same regression output. Now, if you assign lambda or alpha to infinity, then all coefficients will be made 0. All coefficients are made 0. This is a hypothetical situation. You cannot make it to infinity because all the coefficients will then be made to 0. A value of lambda or alpha between 0 less than between 0 and infinity. If you give any value between 0 and infinity, that means 0, 1, 2, 3, any number, you will get coefficients between 0. Some of the coefficients will be made 0. So the alpha value must be between 0 to infinity. Any value between 0 to infinity. So it can be 1, lambda can be 1. For large scale calculations, we'll give lambda 0.5, 0.05. If there are many coefficients, if the model is very big, suppose you have a categorical variable with 20 levels, means you'll get a very large output, right? In such situations, you will assign lambda in multiples of 0.05, 0.01, 0.10, like that, you will assign the lambda values, depending on the complexity of your model. In Kegel house price predictions, we have a lot of variables, right? And each variable has a lot of categories. Each variables also have a lot of categories. Now, each category will be given a coefficient in the regression, right? If you have label encoded the categorical variables, in regression output, each level of the categorical variable will be assigned a coefficient, right? So that means you'll get a lot of coefficients. In that case, the alpha value must be a smaller value, so like 0.1 or 0.05 or somewhere between 0.001 or 0.05. If it is a small regression, you can give alpha value of 5, 2, 3. Let's say you have only 5, 6 coefficients or 10 coefficients. You don't have any problem. You can give lambda value as 5, 20, 10, like that. You can give. But if it's a large thing, you have to give a smaller lambda penalty. So if you are looking at the LASSO equation format, this is the copy image, cell type, not down. Arg mean, y mean is alpha beta whole square, lambda into absolute value of beta, and absolute value of beta square. Two lines represent absolute. This is the formula for LASSO. This is the regression object. Y minus x into coefficient whole square plus alpha into absolute value of beta. Okay, so this is the LASSO regression, also called as L1 norm. LASSO regression also L1 norm. LASSO is a feature selection technique. LASSO is a feature selection technique because it will make some of the coefficients equal to 0. Definitely it will make, if the data is not multicollinear, some coefficients equal to 0. That is the objective of LASSO. The second type of regularization technique, we call it as ridge regression. Ridge regression or L2 norm or L2 penalty. Which adds a penalty lambda or alpha to some square weight or coefficients. Some square weight or coefficients is what ridge regression will do. Ridge shrinks the coefficients to 0, shrinks the coefficients closer to 0, but does not make them 0. It brings the coefficients closer to 0, but it does not make them 0. It is not a feature selection technique. It is not a feature selection technique. Because of this, it cannot be used as a feature selection technique. Ridge is used, ridge regression is used when data is multi-collinear. When data is multi-collinear, we use ridge regression. And the formula is here only we have Ridge and LASSO. Hey, I think I've given wrong formula. It's very saying which formula is this? Argument So this is the ridge regression. Cost is equal to RSSW plus lambda into sum squares of weights. This is the ridge regression. LASSO also will change. This is LASSO. So LASSO is sum of lambda into sum of absolute value of coefficients. Ridge is sum of squares of weights of sum of squares of coefficients. Lambda into sum of squares of coefficients is ridge. Absolute weight of coefficients is LASSO. This is LASSO formula. Okay. The third is the Elasticnet, which is combination of lasso plus ridge. Elasticnet, which is L1 plus L2, or lasso plus ridge. So first lasso will be run. And on lasso output, ridge will be run. Elasticnet is a feature selection technique. So in some models in Python, Elasticnet is by default there. By default is set to Elasticnet. So the alpha value, there is no fixed formula for choosing the alpha value. It has to be done by grid search, or it has to be done by what we call trial and error method. So then, see, we have to do what we call R square and RMS evaluation for different set of alphas. So alpha selection, there is no fixed model. There is no fixed formula to decide that this much alpha for this type of model. It's all more of a trial and error method, and there are new methods which are added. So alpha selection is a method which was added in sklearn, regularization visualization, where we can give a range of alpha here. We can give a range of alpha here, an x-axis, and then this is the error. So what is the best alpha here? Somewhere around 7. Between 6 to 8 is the best alpha. So you have to plot the error and then do it. This sklearn yellow brick is one package of sklearn which is used for finding the correct alpha. Yellow brick is a library part of scikit-learn. Yellow brick is a library part of scikit-learn, where you can use this lasso selection method, alpha selection method. Because there is no fixed model. We have to use trial and error methods. So that is the same thing for ridge also. So in this case, this guy has run alpha with 0, 0.001, alpha with 0.50, and alpha with 10. And you can see this variable becomes zeros. Lot of variables will become zeros. See, with alpha of 10, lot of these coefficients are becoming 0. For 0.001, we are getting coefficients for all variables. For alpha of 0.50, we have some of the coefficients made equal to 0. So by default, 0.50 is the value which is being set in Python in regression and neural networks, whereas we can change that alpha value based on our complexity of the model. So what basically this tells us is alpha beyond 1, alpha above 1 will constantly will make more variables 0. They will be vanishing, which is again a problem to us, right? We will be by facing an underfitting problem, or we might lose some critical variables. So alpha value sometime between 0 and 1 will be a better value, better situation. And in case of 0.50, we have some variables being made 0, but not all. In case of 0.001, none of them are made equivalent to 0. So if you have very small alpha, you will not be able to reduce the variables. You can't use it for feature selection. So in a value between 0 to 1, for a smaller data set, for larger data set, 0.01 to 0.1 would be a better option. So this we have to find out. But there are methods and libraries available in Python which will help us to find the better alpha for our ridge as well as for LASSO. So best would be yellow bricks. I think yellow bricks is already there in sklearn, scikit-learn alpha selection, which is the regularization penalty. We can implement that on data and come up with the better alpha selection. So he is creating lot of alphas. -10 to 1, 400 alphas he has created, but that many alphas we don't want. We can do a better with different alpha methods. So when you are giving alphas, you can give a range of alphas. And the model with the best alpha would be the one which has the least error. So if you are looking at scikit-learn LASSO model, alpha is by default 1. Alpha is by default 1. So alpha is by default 1. Alpha 0 means never give alpha 0. It is nothing but a multiple linear regression model. Alpha 0 means it's a multiple linear regression model. You have to give other than 0. By default is 1. That depends on our data also. No? Sometimes if you give the coefficients, all might become 0. But that's a Boston housing data set. You might have heard about it, no? Boston house data set. It is an inbuilt data set. For that, it is giving all zeros for alpha is equal to 10. You can try it for our Kaggle regression also. So if you look at our Kaggle housewise project, where we can give multiple alphas and we can try to find the best possible alpha. So if you go to the, I think the Kaggle is very open. So from sklearn.linear_model import LASSO. L1 is equal to LASSO alpha is equal to, this is a very large data. So let us be 0.5. L1 model is equal to L1 dot fit x comma y. L1 model dot score x comma y. 85.45. So L1 model dot so I think none of the coefficients are 0. I think instead of zipping, if you do a data frame, that would be better option. Delete our data frame x dot columns comma L1 model dot coefficients. Oh, not all of them are coming. Huh? Okay, not all of them are coming. So I think it is the best option. This is the option. I think none of the coefficients are 0, right? So alpha 20 is not making any difference. Huh? Alpha 100. Alpha 100 is making some of the variables 0. See, basement half bath is 0. Half bath is 0. So alpha 100 is making some variable 0. Same. Score, see, it is not working on your score, right? It is working on your coefficients. It is not working in your R square. It is working on the coefficients. So alpha of 100, you are getting some coefficient 0, right? Some of the coefficients are becoming 0. Here, how many observations we have? We have only 1460 observations. According to regression theory, what is the minimum sample size if you have 79 variables? 20 into 79, 1580. That means we have less number of rows. So you have to reduce variables. Right? So what is the objective here? We have only 40-60 rows. As per the 79 variables, if you remove ID and the dependent variable. So what is the minimum sample size? 79 is equal to 1580. So we don't have 1580 observations. We are not in a position to add rows. So what is the second option we have? Delete variables. We can delete variables by doing a correlation matrix of numeric variables. Find multicollinearity. But to do that, we are not getting any R square above 90. First of all, our R square for base model itself is 82, which indicates there is no multicollinearity. Right? So multicollinearity is out of question. Second is manual selection. For manual selection, your judgment might be right or might be wrong. Best option is LASSO. LASSO alpha is equal to 100. It is eliminating at least two variables, right? Or more than two. So 1, 0, I see 2 zeros. Any other zeros? 3 zeros are there. Street is also 0. Here, central air is 0. So garage quality is 0. Fence is 0. Right. So at least 5 to 6 variables it is reducing. So if it is reducing 5 to 6 variables, then our sample size becomes relevant. So that is what we have to do. So here we have a good model, no doubt about it. But the basic requirement of sample size is not met yet. So that is why we are trying to reduce the variables. With alpha 100, we are able to reduce variables. Feature selection, not dimensional reduction. This is feature selection. Feature selection is done by eliminating certain variables. Selection is done by eliminating. Reduction is done by combining. That is the physical science, scientific terms. No? Selection is always done by elimination. By eliminating something, you select. Reduction is done by merging or combining them or grouping them into one. So with alpha 100, we are reducing the variables. So here we have a good model with 85.31 accuracy with reduced variables. I think if you submit this score to your Kaggle competition, you will have a better score compared to a regression score. Compared to regression, LASSO is a better score. Now you can run Ridge also, but Ridge does not eliminate variables. That will only shrink the coefficient size. Ridge is not relevant here because there is no multicollinearity. There is no multicollinearity, so Ridge is obviously not the right choice. You can try Elasticnet. If you want, you can try Elasticnet with alpha of what you call same 100 alpha. You can try. For Elasticnet, convergence happened. Did you get any warning? Warning came, huh? Convergence warning. So convergence warning means all the coefficients could not be calculated. So you have to, what is the alpha you gave? 100. You have to increase the iterations or consider increasing regularization. Make it alpha 200. Warning also came, huh? So this guy has built a model with Elasticnet. Alpha MP range 1e minus 4, 1e minus 3, 1e minus 4, L1 ratio of 0.11, max iteration is 1 lakh. Yeah, most of them will try and take the idea from Google only. Score is 956, RMS is 01. So with Elasticnet, so you can try Elasticnet with this option. Alpha of 1e minus 4, then max iteration is 1 lakh. Without warning. Alpha 200. Let us go with alpha with 100 only and max iterations. This EN model is equal to EN dot fit x comma y. EN model dot score x comma y 76.02. But we need to check how many coefficients are made to 0. There x dot columns comma EN model dot coefficients. Are there any zeros here? 0, 0, 0. So I don't see any zeros here. There are zeros. Slot configuration is 0. Utilities is 0. Okay. Then only 2, right? Slot configuration and utilities are zeros. MS zoning is also 0. 0. MS zoning is also 0. Any other? Then I think we should go with 200. Then we have additional value 0. What is the score we got? 75.65. Then let us see. Now we have more variables 0. Half path 0. Land contour 0. Configuration 0. Then what else is 0? Utilities 0. Heating 0. Paved drive is 0. Garage condition 0. So 200 with max iterations 1 lakh, we are getting 0. We are having feature selections. And we can build a regression model of this, or we can do a weighted average of all the models. It is about 0.60. See, we might sacrifice, see, that's what now. Sacrifice bias and variance. You need to make some sacrifice. Either you sacrifice variance for bias or bias for variance. These are bias models. So we are sacrificing variance. So if the model is least variance, we are happy because these are all biased models, right? There are assumptions. All the regression assumptions are valid for LASSO, ridge, and Elasticnet, which is closer to normal distribution, numerical continuous, no multicollinearity. All these things are there. Linearity, exogeneity, residual homoscedasticity, residual normal distribution, all things are there. Okay. So I am emailing the files. Madam. Page Elasticnet overfitting and under